Hello, welcome to our fourth video about abstract interpretation, in which I will speak about termination and safety of our algorithm. The results I will depict in this video are the following. If we have strong structural properties about the design of our abstract domain, then we will get termination of our fixed point algorithm as well as soundness, which is that the abstract semantics we will compute using our fixed point iteration will be a sound approximation of the concrete semantics for all the control points of our program. Before taking the next slides for demos, let's make a quick remark. The sign domain we saw in the previous videos was of finite height, and I'll let you think about the arguments in favor of that property of the sign domain. Let's begin with termination. So termination comes from the fact that all the sequence of the abstract states we are computing are increasing, and they rely on lattices on the finite height, so it cannot strictly increase inside these lattices. Thus, it converges in less than the height of the hash diagram steps, so we have termination, of the sign abstract domain. Now that we have termination, let's look at soundness. First of all, I recall a theorem that says that if we have a monotonic function on a complete lattice and a sequence of iterates that is ultimately stationary, then the limit that is computed is the smallest fixed point of the function. So the proof of that theorem is left to the reader. I just want to focus that here we have complete lattices. F, the functions, would be the transition functions of our program, and it's easy to see that these functions are monotonic. For lattices of finite height, we already proved that the sequence is stationary, so it would mean that the limit we are computing is the smallest fixed point of the function. What does it mean? It means that if we go to our complete lattices here, and we come back to the function here which define each step of our algorithm here. This function is monotonic because sets are ultimately growing. These are computable since we define all the operations to be computable. The theorem says that if the sequence coming from the initial set of abstract valuation is stationary, our method gives the abstract semantics, which is exactly what we want. Moreover, we have soundness. If the computation terminates, the results that we have here, the R# that we compute, is bigger than the concrete value it represents. So that's exactly what we are searching for, a bigger set of behavior that we had before. So let's recall a bit. We had the program points here, which is a set of behavior of the program, which was in dark gray. And here we are computing from R# a gray set, which is bigger than the behaviors of our program. And we are computing this set by a finite computation in some special cases. I'll let you look at the proofs. The proof is not so difficult, so I'll let you make this induction proof properly. Now that we have finished with these theorems, I give you an example of a non-relational abstract domain, which are constants. Here is the hash diagram of constants. From that S diagram, you should be able now to give alpha and gamma, and the whole alpha and gamma from the whole domain of constants. Prove that it is of finite height, and then use the previous theorem to make a constant propagation analysis, which gives you an over approximation of the behavior of the program in terms of constant values. These constants propagation is used for constant folding inside compilers. In the slides, we also give you an example of computation inside this abstract constant domain. I go quickly in the rest of the video. You can do it by yourself. At that point, we have reached the fixed point, and finally it means that we have proved that the concretization of 15 here at the control point 3, which is 15, so we have proved that y is always equal to 15 at this control point. Now let's say a few words about implementation, especially about the implementation on the real world versus the implementation on your lab. In the literature, we see two abstract interpretation implementation choices. What we've done is somehow an implementation inside the control flow graph, which computes one abstract value per block or per control point, and which relies on the propagation on the edges of the control flow graph. This computation is based on the small step semantics of the program, so it's called small steps abstract interpretation. We have another solution to apply abstract interpretation, and that's the one we will choose in the lab. On the abstract syntax tree, we can use a visitor and do the propagation by induction on the syntax, which means that you should define your abstract interpretation in terms of big step semantics. But it means that you have less choices to make inside your implementation, and the implementation is easier to do. Concretely, it means that to interpret your program, you begin with all possible values for the valuation, and then for each instruction, you do what you have to do. So let's focus here on the test here. To compute the effect of if B then S1 else S2 on the current abstract value, you should compute the effect of the test on the current abstract value and compute this abstract semantic of S1 applied to this new set. Then for the negation of B and S2, and then make the union of these two contributions, basically like we were doing the union in the control flow graph there. For while loop, you do the same, and a while loop basically means to make abstract unions of the former abstract value and the one abstract effect of the loop you have just computed. Of course, we should test for stabilization. Okay, and what I claim is that you only should test for stabilization inside the while loops, which is clearly easier than making a test of stabilization for all sets for all control points of our programs. And at the end of the stabilization here, when you have returned your abstract values, there still remains something to do with assertions. So what are these assertions? I will call the big picture for proving facts about programs. We have these concrete semantics of programs that are usually uncomputable. All about abstract interpretation is to compute the abstract semantics here in gray. So this is done on the previous lines. And then we should define acceptable behavior. So acceptable behavior will be done by adding program assertions. For instance, assert that x is greater than 0. And when you come to this point, you check that the abstract value you get is included inside this new abstract value. Of course, to use asserts, you should augment your language syntax and semantic with these asserts, and you should also implement the tests inside your analyzer. In conclusion, we have seen that to make program analysis with approximation, there is a great domain that is abstract interpretation that permits to have a general framework in reasoning about abstract programs. Abstract interpretation defines a generic way to compute invariants with a fixpoint algorithm, and this fixpoint algorithm is parameterized by an abstract domain. So this is a cool generic framework with theoretical results that permits to get strong results like termination and safety, if you are able to prove some properties of your abstract domain. So be careful, for the moment we didn't cope with infinite edge lattices nor relational domains. So this will be done in next videos. Bye bye.